Thank the organizers for the invitation. This talk is on geometric structures on complex manifolds, and it's a joint work with Indranil Biswas. So first, let me define this notion of geometric structure, which is a holomorphic Cartan geometry. And I will start by drawing a picture, which is a short pass in the history of geometrical structures. So let me put things like this. First, geometry we all think about is Euclidean geometry. And starting with Euclidean geometry, we have several kinds of generalization. First one, which comes from the work of many people, but that put Gauss and Riemann, is the generalization of what we call now Riemannian geometry or Riemannian metric. So here, you change the standard inner product in a smooth family of inner products, and you allow some curvature here. So you allow curvature. And this curvature will be zero if and only if you are locally isometric to the Euclidean geometry. Another generalization of the Euclidean geometry is given by Klein in the context of homogeneous spaces. So the idea here is to look to the symmetry group of the geometry and to say that, in fact, of course, for the Euclidean geometry, you will have G as being the group of Euclidean motions, and H is the stabilizer of the origin, the orthogonal group. But you can look in generally to all these models, which are G over H, where G is a finite dimensional Lie group, and H a closed subgroup in it. And here comes the work of Cartan. For each homogeneous space, you define a Cartan connection of Cartan geometry with model G over H. So here, the infinitesimal model will be G over H, exactly as the Riemannian geometry has the standard Euclidean geometry as model, as infinitesimal model. So here also we'll have a notion of curvature. And the curvature will vanish exactly when you are locally isomorphic to the homogeneous space. So in this talk, we will have a manifold, which is a complex manifold, smooth complex manifold of complex dimension n, and G is a complex Lie group, and H is a closed subgroup. For example, here in the complex setting, the notion of the Euclidean geometry will be a notion of complex Euclidean geometry. So the model will be Cn with the standard quadratic form, the quadratic form of rank n on Cn. And as homogeneous space, G will be the semi-direct product of the complex orthogonal group with Cn acting by translation, and here H will be the orthogonal group. The associated holomorphic Riemannian metric will be something which you can obtain if you have Gij, which is real analytic. You complexify locally, and you put here a complex coordinate, and you have something which is like a holomorphic Riemannian metric with the tensor, the curvature tensor will vanish if and only if you are locally isometric to this constant quadratic form. Other examples to think of are G, the complex affine group, which is semi-direct product of GLN with Cn acting by translation. And another interesting geometry will be the projective geometry, where G is the group of projective transformation, and here X will be the projective space. So these are three interesting examples of geometry for which we will define the holomorphic Cartan geometry on M associated to those models. So the definition will go like this. Definition. So this is Cartan definition. A Cartan geometry on M will be the following data: a holomorphic bundle with fiber H. So this is a Cartan geometry of M with model G over H. You need to think that this bundle generalizes the canonical fibration of G over H. So you ask to this H principal bundle to admit a form with values in the Lie algebra of G. This is the Lie algebra of G with the following properties. First, you ask omega to be a vector space isomorphism at any point. So the holomorphic tangent bundle to P will be trivialized by omega constant holomorphic vector fields. You ask this to be an isomorphism at the level of vector spaces. The second property is that in restriction to each fiber, what you see is the molar Cartan form of the Lie group H. And the third property is some compatibility with the H action on the bundle when you take the action of an element H on omega. It's like the adjoint representation of H. So this is this compatibility with respect to H action on P. So I call it right action. What does it mean exactly? Is that this means that you have a parallelization of the holomorphic tangent bundle of P by omega constant vector field. This parallelization in general is not a Lie algebra isomorphism, but it's a Lie algebra isomorphism restricted to each fiber. In restricting to each fiber, omega will send H invariant vector fields on the Lie subalgebra H. So at the level of each fiber, you have a Lie isomorphism. Moreover, the third condition says that if you plug inside two vector fields, one of each is vertical, then the Lie bracket agree on the manifold and on the Lie algebra G. In general, omega will not be a Lie algebra isomorphism, and the curvature is the obstruction for omega to be a Lie algebra isomorphism. So the Cartan theorem is the following. You compute the curvature as being the obstruction for omega to satisfy the molar Cartan equation in the group G. This is a two-form on P, but as we noticed, if you plug inside a vertical vector field, it will vanish. So this two-form lives on P, but is basic, descends on the basis manifold M. You can think of it as a two-form on M. And Cartan theorem is the following. If this two-form vanish, then it's an if and only if condition. Your bundle P is locally isomorphic with the standard fibration of G over H endowed with Morel Cartan form of G. So in this sense, this definition will generalize that of a homogeneous space. Moreover, we have a nice geometric description given by Ehresmann. So trying to understand Cartan's theorem, Ehresmann gives the following nice geometric description of the flat case. So he proved the following. K omega is 0 if and only if the following bundle, which I call PG, which is obtained starting with P by extension of the structural group to G, endowed with a one form which I will define, is flat. And omega tilde is once again one form with values in G, which is obtained in some canonical way described by Ehresmann from the Cartan omega form. So I wrote here this equation, and the idea now is the following. You had a H principal bundle, now you have a G principal bundle with a one form with values in the Lie algebra of the structural group. We have what we call now an Ehresmann connection. And this omega tilde was constructed in some natural way. For example, you can see that on P times G, this omega tilde vanishes on H orbits, and it's H invariant, meaning omega tilde is a form on the bundle PG. Now you have what we call a flat principal bundle. You get a flat principal bundle, and this flat principal bundle means that the kernel of omega tilde, which is a horizontal distribution, is integrable. So the curvature of omega is 0 if only if the curvature of omega tilde is 0. And with this description, we see that, in fact, this G principal bundle in the flat case gives you some monodromy. So you are now in the situation of a G principal bundle. So now the Ehresmann description of the flat case, you have a flat principal bundle, so you get some monodromy from the fundamental group of M into G, which is the monodromy morphism. If you pull back your flat bundle on the universal cover of M, it becomes trivial. So the pullback on M becomes trivial. And you have the following picture. You have M tilde and G. And now you have to remember that your bundle have a H subbundle, because you constructed it starting with a H bundle. So you have some section which is a map from M tilde into G over H. So you have a flat G principal bundle. You have also a flat G over H bundle associated to it. And this G over H bundle, so with fiber the model G over H, admits a section which is called the developing map. This section comes from the fact that you have a reduction of the structural group to H. Moreover, this developing map here is a local diffeomorphism between your model G over H and M tilde. This comes from the construction of omega t. Yeah. Yeah, so you mean...
I would like to start with,
yeah. So, so the description is the following. You can say the following. It's the same way to say, same thing to say a flat X bundle, sorry, a flat bundle, a flat G bundle with fiber X and transverse section. Or a flat G bundle with fiber X, which is the homogeneous space. And this is the question.
So suppose you start with non-flat distributions and you get this omega t.
So in general, this omega tilde will be, the kernel will be a distribution. You can have developing maps over curves. You can lift curves and project them on G over H. So it's the developing of a curve. But in the flat case, you can even lift simply connected sets from M and develop in G over H. Now, I would like to stick with Bruno Klingler's definition of bialgebraic because he was so general as usual. And if you want to stick with this definition, we'd like to have something more general, where the homogeneous space does not always have the same dimension as M, and the developing map is not always a submersion. So in this case, you need to put here a generalized Cartan geometry. And then you need to skip the first condition. Just skip this one. Then everything works. This Ehresmann connection, omega tilde, is a genuine Ehresmann connection. The only thing which do not work anymore is that this map from M tilde to G over H is not a local diffeomorphism. In fact, the rank of the differential here will be the rank of omega minus dimension of H. And with this new definition, in the flat case, you will have a map from the universal cover into the model G over H, which is equivariant with respect to some monodromy morphism. This new definition of a generalized Cartan geometry is stable by pullback through any holomorphic map. If you take the pullback through a ramified map, you will find something which is nice in the sense that omega will be an isomorphism on an open-dense set. So you have a notion of more geometric generalized Cartan geometry, which would be, let's say, branched Cartan geometry. And in this case, you replace first condition by omega is an isomorphism on an open-dense set, which will be H invariant by the third condition. For example, you take any projective manifold. There are finite maps into the projective space of the same dimension. You pull back the standard projective structure through this ramified map. You will get on any projective manifold flat, branched, complex projective structures. So usually when you ask to your Cartan geometry to be holomorphic everywhere and a genuine Cartan geometry with first condition omega and isomorphism, there are few compact manifolds admitting this kind of structure. But there are much more of them if you allow some branching conditions. now, this very general definition given here, in the three cases I gave, like complex Euclidean space, affine space, projective space, you find the usual condition of for the affine space, you will find a holomorphic affine connection, and the H bundle will be the frame bundle of the manifold, GLNC frame bundle. For the projective space, you will find the holomorphic projective connection, and H will be the projectivization of the tangent space of the manifold. And for the complex Euclidean geometry, you will find something which is completely equivalent with a holomorphic Riemannian metric. In each point, you have a holomorphic quadratic form on the tangent space, which is non-degenerate. And the H bundle will be the bundle of orthonormal frame for this holomorphic Riemannian metric. Now I will give you some results when you assume that some results about Cartan geometries and generalized Cartan geometries when you assume that the manifold is simply connected. Those results were somehow motivated by the following question. The question is the following. Let M be a complex, compact, simply connected manifold. With Cartan geometry of model G over H. Is it true that M is biholomorphic to G over H? Meaning, if you admit a Cartan geometry, is it true that the manifold will admit also a flat Cartan geometry with the same model? And in this case, the developing map gives you identification. For example, the question is open. In general, for the complex projective space, we would like to have a characterization of a complex projective space, which is non-metric, it's the only compact, simply connected complex manifold with a holomorphic projective connection. Sub-question of this example: is it true that simply connected manifold does not admit holomorphic affine connection? Of course, here the model is affine, so if we think that the question is correct, simply connected manifold in general will not admit holomorphic affine connection. And there is some evidence going into this direction. First evidence, the answer is yes for Keller manifolds. If M is Keller, let's put things like this. Assume that you have a holomorphic affine connection on M. Then you can compute Chern classes of the holomorphic tangent bundle using the holomorphic connection by Chern-Veit theory. And you get some representative, which is a 2K0 form on the manifold. But if you do the computation as usual with the Keller metric, you will have a representative, which is a KK form on the manifold, meaning that all Chern classes of a vector bundle with a holomorphic connection over a Keller manifold vanish. If this bundle is the tangent bundle of the manifold, you know by Yau solution of Calabi conjecture that there is a Ricci flat metric. And since the second Chern class vanish, this Ricci flat metric will be completely flat. And by Bieberbach theorem, M is covered by a torus. So in the Keller case, the only holomorphic connection in the tangent bundle exists on tori, and they are translation invariant. So the question makes sense for non-Keller manifold. And let's also keep in mind the following thing. The vanishing of the Chern classes of vector bundles with connection over Keller manifold was proved first by Atiyah, and he asked if there is some flat connection also. So there is this Atiyah question, because there is no homological obstruction to find a flat connection of the manifold. And in general, this question is open. If you have a holomorphic connection on a vector bundle of the manifold, you have also a flat connection. The answer is yes for the tangent bundle, but we don't know the answer in general for any holomorphic vector bundle. I will give some partial answer today. Also, the answer is yes to this question if the algebraic dimension of the manifold is 0. This is a common work with McKay. I will explain why the algebraic dimension 0 makes things easier for this kind of study of geometric structures. And now let me give some results which go into the direction of those questions. So our results with Indranil are the following. Once again, you assume the manifold is simply connected. And M is compact complex. First theorem. They do not admit holomorphic Riemannian metrics. No holomorphic Riemannian metrics on M. Meaning we are not able to do the general case of holomorphic affine connection, but there are no holomorphic Riemannian metrics on simply connected manifold, even in the non-Keller case. Let me say that in the non-Keller case, there are nice examples of manifold admitting holomorphic Riemannian metrics, which come from deformation of parallelizable manifolds. Is it clear, the statement? Sorry, yeah. Sorry. Yeah, twice. Twice. You're right. You're right. So here, M, non-Keller, so general. Theorem 2 with Indranil. Here we assume M is in class C, meaning that M is bimeromorphic with a Keller manifold. It's also simply connected. And M admits a holomorphic Cartan geometry. Then M is projective. This theorem 2 go into the direction of Borel-Remer theorem. If you, yeah, class C means Fujiki class C means meromorphic image of a Keller manifold, and it's the same as being bimeromorphic by Varushkas. And This goes into direction, if you think our question is correct, homogeneous manifolds, which are in class C, are products of a projective rational manifold with a tori. And in the simply connected case, you don't have the tori part. So you have also this projective rational manifold. So this goes into this direction. For example, this settles the case, this generalizes to class C, the result about connections. Because on class C, you also have the same proof of the fact that Chern classes vanish as soon as you have a connection. And now your manifold must be projective. So it's like in the previous case. So it somehow generalized the case of connection to class C manifold. And the third result work for any, which is with Indranil also, work for generalized Cartan geometry. For all those, and this is the following. Once again, M is simply connected, and if M is Calabi-Yau manifold, meaning Keller-Calabi-Yau, Keller manifold with, so meaning Keller, and the canonical bundle is trivial, then any generalized holomorphic Cartan connection on M is flat. Flat means it will be given by a map from your simply connected manifold into G over H. This, of course, gives you many non-existence theorems. For example, if G over H is affine, you don't have any, even in higher dimension, assume G over H has higher dimension, but it's affine, you don't have any non-trivial map from M to G over H. Assume now that you are in the standard case where G over H has the same dimension as M, and the map, which is the developing range, is a submersion. You don't have submersions for compact, simply connected Calabi-Yau manifold to homogeneous space. There is no such submersion. So there are no genuine Cartan geometries on simply connected Calabi-Yau. For example, we have seen that any projective manifold admits branched projective structure. Conversely, take a Calabi-Yau manifold modeled on the, which admit a complex projective connection. It must be flat, so it's given by some ramified map from the manifold into the projective space. This implies that your manifold is Moisheson. You pull back meromorphic function from the projective space. You have many meromorphic functions. It's Moisheson and Keller, so it will be projective. So it's for among all Calabi-Yau manifolds, those which admit branched projective structures are exactly those which are projective. It's a consequence of the result. Okay, are there questions about the statements? Okay, so if not, I will give some hints about tools one can use in this. Sorry. Yeah, you're right. It's a section. So you're right. Could be put like this. It's a section such that G is non-degenerate at each point. But you are right. It's a vanishing theorem for a very special geometric section. one could ask, can we do something for section which degenerates somewhere with a divisor where and I have examples on non-Kähler manifold where such things exist and they have less symmetry than those, but I don't have simply connected examples. So maybe your first theorem could work also for branched holomorphic Riemannian metric, meaning sections which are non-degenerate on an open dense set, but I do not have the proof. Could work. And very good question, because in fact I gave this definition of holomorphic Cartan geometry, and by equivalence principle of Cartan, holomorphic Cartan geometry modeled on the complex Euclidean space is the same as this kind of section, as the Riemannian metric. But we do not know exactly how is the equivalence in the branched case. I gave this definition. If you give me some degeneracy here of a section, I'm not able to say in general if it's equivalent with the definition with bundles. Some of them are. For example, when you pull back by ramified maps, regular objects. But in general, there is not known this equivalence principle for singular objects. Here it's equivalent because it's non-degenerate everywhere. Okay, so somehow the methods are similar for the first two results and different for the second. Yeah. I must be very clear about this. That's why this result is a particular case of the question about affine connections. Because as Claire said, those objects come with a geometry. They have a Levi-Civita connection, which is holomorphic, and you compute curvature with this holomorphic Levi-Civita connection. Moreover, you can see that this holomorphic quadratic form gives you an isomorphism between the tangent and the cotangent bundle. So you can say that canonical bundle and anti-canonical bundle are isomorphic. So the canonical bundle is with torsion, order 2. But on simply connected manifold, you can assume it's trivial. So it's somehow like non-Kähler Calabi-Yau, the trivial canonical bundle. Of course, it would be nice to have this result for any connection, not only for holomorphic Riemannian metric. So let's see how the hypothesis on simply connected manifolds will work here. And this comes from the study of the symmetry of this geometric structure. So there is a notion of symmetry here, which is the generalization of the standard notion of a killing field for a Riemannian metric. I will say that a holomorphic, say local, vector field on M is said killing if it lifts to the bundle P as X tilde, and the flow, the local flow of X tilde acts by local automorphism of P omega. So this is a general definition of a symmetry for a Cartan geometry. So there is a unique way to lift a killing field on the manifold M on P in order to act as P automorphism. But what is not clear is that you are able to preserve omega. But this is exactly what you expect as standard definition for a vector field to preserve a tensor as a holomorphic Riemannian metric or a connection. Is your standard way to define symmetry for such objects. And maybe, and this is general fact, fact one, which is due to, first to Nomizu, but then proofs were generalized by Amores and Gromov. Local Killing fields of Cartan geometries on simply connected manifold extend to all of M, meaning that any local symmetry of such a geometric structure, for such a or holomorphic connection, for example, it's globally defined. You don't have obstruction. The only obstruction is the topology. As soon as you are simply connected, and those vector fields, in fact, in general, is a sheaf of vector fields which is locally constant. And the fiber is a Lie algebra, a finite dimensional Lie algebra. Of course, the hard by analytic continuation, yeah. You have, in the smooth case, of course, this is not true. You can make a bump and, yeah. This is a real analytic category. But of course, if you have a germ of geometric structure, in general, you don't have symmetry at all. So the point is to show that when you are on compact manifolds, you have symmetries like this. And this is given by the second fact, coming from the work of Bogomolov and Gromov. So, coming from their work, you can prove the following. You take the manifold M, and then you look to what we call the algebraic reduction of M. So there is some model M tilde, M psi, a bimeromorphic map. And then the projection on a projective manifold. In such a way that when you pull back meromorphic functions from V, you will get, all meromorphic functions of M. Meaning that if you have a manifold which is not projective, you will have less meromorphic function as in the projective case, but all of them come by pullback from a projective manifold. And the fact two, this is very general fact about complex manifold. The fact two put together the Cartan geometry with this algebraic reduction, saying that local Killing fields, this work in general, even for non-simply connected manifold, act transitively on fibers of the algebraic reduction. So this theorem say that, for example, if you don't have at all a meromorphic function, if you don't have non-constant meromorphic function, what we call algebraic dimension 0, because V will be a point, then those local Killing fields will span the tangent space at the generic point. So there are many of them. If you put together the fact that you are simply connected, this gives you a Lie group acting with an open dense orbit on your manifold. As soon as you have a Cartan geometry, your manifold will be almost homogeneous. Why there are three of them? You would like for this map to be a morphism with connected fibers. In general, you cannot get it on your manifold. You need to change the model. But I think you can think intuitively that you don't have the second guy. Sorry? Yeah, you can put m tilde to m if you want, but it's, yeah, it's a bimeromorphism. The map is the other way, yeah? Sorry. Like this, yeah? Okay. So I should do this and say that here the reduction is, you're right, okay. So what I'm saying is you have local symmetries. You have local symmetries as soon as your manifold is not Moisheson. As soon as the fibers of the algebraic reduction have positive dimension, you have some local symmetry. Oh, okay, so I can give you the proof, but basically this is the following. Okay, I give very short proof. The Gromov thing is if you want to find local isometry, you look to jets at finite order. If at two different points with big order you have the same jet, they are related by local isometry. Okay. So what you need to study is jets of finite order of your geometry. And there is some algebraicity here. The action of H on the finite order of the geometric structure is algebraic. So you have some Rosenlich theorem. If you have different points in different orbits, you separate by meromorphic function. So if two different points on your manifold have different jets at order k, you will find a meromorphic function on your manifold with different values in these 2 points. So this is Gromov and Bogomolov thing. Okay. So points which are not related by symmetries are separated by meromorphic function. So on projective manifolds, you cannot say anything, but there are already some results. In algebraic dimension 0 gives you a lot, gives that you are locally homogeneous on an open dense set. But on simply connected case, that means almost homogeneous, and almost homogeneous manifold cannot have a trivial canonical bundle. So this, you will get rid of the algebraic dimension 0. But now, what happens if your manifold is Moisheson? This is somehow the hard point where you don't have local symmetries. Assume your manifold is Moisheson. This will not be useful in the Moisheson case. But what happens in the Moisheson case is that Moisheson manifolds, meaning that the algebraic dimension of M, which is dimension of V, is also dimension of M. You have the fact that if M is not projective, there exists F from P1 of C into M such that F non-constant. So you have copies of P1 of C in your manifold if it's Moisheson but not projective. And then you look to the differential of F going from the tangent space to P1 of C to the pullback of Tm. And you notice that the pullback of Tm admits holomorphic connection. But holomorphic connections on symmetrically connected manifold means that the manifold is trivial. And you have here some contradiction because the degree of the tangent bundle is positive. So in fact, you don't have any morphism like this. This implies F should be constant. So the manifold is projective. So you are not in this case. So here, this is very general. A manifold with a holomorphic affine connection do not have P1 of C inside. No rational curve. It's general. Now, what happens? You really have V, which is of intermediate dimension now. So we have, there exists, let's say, the following. Assume, this is an easy case. Assume the algebraic dimension is 1. When the algebraic dimension is 1, the fibers have dimension n minus 1. So you have n minus 1 linearly independent vector field, which you put together with a section of the canonical bundle and gives you a one form, which vanishes on the fibers of the algebraic reduction. This one form is basic, it comes from the algebraic manifold, so must be closed. This is the contradiction. You get a closed one form on the manifold. And in fact, this is very general. Any geometric structure on a manifold with algebraic dimension 1 and trivial canonical bundle has this property, so you don't have any geometric structure on those manifolds. Not only holomorphic Riemannian matrix, but you assume a trivial canonical bundle. And in general, you do the same. You will find here, when you assume the algebraic dimension is K, then you will find x1, xn minus k vector fields. And for each one, you consider the dual form. And you want to find one dual form which vanish on the fibers of the algebraic dimension. And you do in the following way. You have a volume form on this manifold, a real volume form, which is omega wedge omega bar. If the automorphism group of a manifold with a finite measure is non-compact, you can apply Poincaré recurrence theorem, and you find that one of those vector fields must vanish somewhere. If it vanishes somewhere, the dual form vanish on all those vector fields, so vanish on the fibers of the algebraic reduction. This is finished. In the case where the automorphism group is compact, you will get a fibration by tori over a projective manifold, and you finish by using this fibration. So this is the idea of the proof. I will not have much time. I would like to say one word about the last theorem, about the theorem on simply connected Calabi-Yau manifolds. What we do in this case is that we prove Atiyah question for simply connected Calabi-Yau manifolds. So we prove the following lemma: let M be a compact, complex, simply connected manifold, simply connected Calabi-Yau manifold. And E, a holomorphic vector bundle over M. Then, if E admits a holomorphic connection, then E is trivial. And the connection is the trivialization. This is the fact that if those manifolds, these bundles admit a connection, we prove that they admit a flat connection, so they are trivial. And the idea of the proof is, in fact, we use a Simpson result proving that E is semi-stable. And in the projective Calabi-Yau case, it's enough to prove that the first two Chern classes are zero and that the bundle is semi-stable in order to know that it admits a flat connection. In this case, flat connection means it is trivial. And since on those simply connected manifolds you do not have forms, on the trivial bundle you only have one connection, the trivialization. There are no non-trivial forms. So what we prove is that E is semi-stable. In fact, in the Keller case, the Simpson criteria is more involved. You need to prove that there is some filtration with successive quotients which are polystable of degree 0. So we did this. But in the semi-stability can be proved by showing that if you have a destabilizing subshift, it will be invariant by the connection. Then we prove that any subshift invariant by the connection is a subbundle. So it's of degree 0. So it's not destabilizing because of degree 0 like E. So this gives semi-stability. And then we apply Simpson criteria. Here we need Calabi-Yau assumption twice. One, we need Calabi-Yau assumption to prove that the destabilizing subshift is invariant by the connection. We look to the second fundamental form, and we need to prove it's 0, and we use Calabi-Yau. And Simpson criteria also use Calabi-Yau. Yes, what's the relation between the geometric structure and this bundle? In fact, the point is to consider G and a representation of G with discrete kernel, which does not exist always. That's why there is some hypothesis. In fact, G in the Cartan geometry must be complex affine, must admit this property. Because if not, in fact, if G is an elliptic curve or a torus, there are counterexamples of this. So in fact, there is some hypothesis, in theorem 3, you need to put that the Cartan geometry has a model G such that G is complex affine. For example, it works for simply connected groups or for semi-simple group. And once you do this, you associate to your G bundle of the geometry, for which you want to prove flatness, a vector bundle with a connection. You prove flatness for the connection. The curvature is the same because it's injective to the level of Lie algebras. So you prove that, in fact, your starting G bundle had a flat connection. Your connection was flat. So you need this hypothesis, which is satisfied for all reasonable geometric structures, that G is complex affine, admit representation with discrete kernel. So thank you for your attention.